Welcome. Welcome, everybody, to a Literature Review Tuesday. We're looking at the top of Phys Review letters today. Because we were looking at the top of Phys Review letters last time. Ooh, getting that literature review started right. It's a little peanut punch. Oh. Yes, it is 10 o'clock a.m. Pacific. Not starting on time again. Not starting on time. We've been later than this, you know? We've definitely been more on time than this before. And we've certainly been earlier. Hello! But we are here nevertheless. Let's dive right in. Oh. We got some fun, funky music here. I didn't say it was good music. Fun and funky. Just talking? Coding? This is pretty good. Cool. I mean, I could be bigger, I guess. I could be bigger. Or should I just do like a different scene for this? Yeah, let's do a literature review scene. Lit review. Nice. Okay, and in lit review, I can be a little bigger. So can the text. If I end up covering essential text, let me know. We'll fix that up. These are some groovy beats. Okay, but they're a little loud as well. Yeah, we want these beats under control. Like, it's nice to have a little background music. What does this sound like here? Let me check it on another device. Hold on. Let's absolutely check the levels here. Yes, we're doing a little background music today. A little DRM-free chill vibe. Mostly for me. Nice to have those chill vibes while I review literature. And welcome and good morning. Top of Phys Review letters, both because physical review letters provide some of the best particle physics content, but also because it just provides a general overview of technological advancement at the theoretical level, which really helps you to see the future of the technology landscape a little more clearly than you would for, I don't know, different journals have different impact, let's say. Okay, let me check the levels here. Just relax. Sit back. Get yourself a little peanut punch. Anything to quench the thirst. Oh, it's all chillin' here. You can tell we've read a lot of articles already. Here, I'll squeeze this over so you can see the number of citations, but 2,200 citations on that positive muon anomalous magnetic moment measurement. 2,200. People were dying for this publication. We've been waiting a long time. I just kind of want to draw like a word cloud of these ideas. Do you have draw.io? Yeah. Try to remember the impacts of the big journal articles at the top of Phys Review from last time. What were they? What for over the last 5 years? Yeah, the muon magnetic dipole measurement. Anomalous. Discovered. This is big. 2,200. 2,200. Right? Citations. Huge. And then it's a groundbreaking discovery in astronomy. It's the merger of two black holes into one black hole, 150 masses of the sun, 150 million masses of the sun. And that was thought to not be able to be possible. It was thought that when those two very large entities came together at the scale they did, 60 to 80 million solar masses, that it would result in an explosion and a repulsion of the net aggregates. But instead, we saw a merger, an enormous merger. And if you check the list of the largest objects known in the universe, this new object ranks somewhere around top 5. So it's huge. It was the merger of an 85 and 66 million solar masses, or is it just solar masses? I think these are... Well, let's just ask ChatGPT if it knows the notation. What does mean? What does mean? It's an astrophysics notation for the estimated mass with asymmetric uncertainties. It means the best estimate is 85. Okay, it's not million solar masses, excuse me. It's 85 solar masses. So it's 85 times the mass of our sun. And the upper uncertainty on that mass is 21. The lower uncertainty is negative 14. So the actual value is likely in the range 71 to 106 solar masses. So we don't have the exact mass of these objects, and we have very high uncertainty. Cool. Did they say anything magnificent in the abstract? No, it's very technical. Yes, and the tone is that it sets the goals for future literature. It sets the goal for existing experiments to focus their models and improve their models to encompass and encapsulate this observation. And it could be a very statistically unlikely event, but there you go. Black hole merger, 1,400. Black hole merger, 150 solar masses. I don't really have the icon for solar mass here, but can I paste? I can paste the image. Oh yeah, there we go, this guy. What if we just lock these together? Yeah. Lock. Nice. Oh, it's locked in place. I wanted to group these. That's what I want. Group. $1,400 citations. Yeah, huge. What else was huge? I think there's some semiconductor business going on. Oh, the quantum computer. Strong quantum computational advantage using a superconducting quantum processor. If I recall, they reduced the speed of a problem from today's supercomputers taking 8 years down to an hour, 1.2 hours. What would have taken 8 years, they did in 1.2 hours. And that sampling task, does it tell us what the sampling task was? And the size, 56 qubits and 20 cycles. How many citations on this paper? Yeah, 1,300. It's huge. So a few less on the black hole merger. The number of citations a paper has is also a function of how long it's been in the literature. If you're starting to get on in your age, you'll accumulate a very large number of citations. But if you're a brand new paper, you'll have very few. So it's misleading even to resize these. Let's leave them big the way they are. Nice. Okay, ungroup. Let's delete that. Quantum computer. How do I paste and match style? There we go. And that's 1,300 citations. Okay, and then it's some quantum discoveries. It's the topological origin of non-Hermitian skin effects. These are effects that arise naturally out of the mathematics that underpin quantum mechanics, and now we have observations of those skin effects. It's a unique feature of non-Hermitian systems, which is an extreme sensitivity to the boundary conditions. That's why they're called skin effects. Here, they reveal that skin effects originate intrinsically from intrinsic non-Hermitian topologies, and such a topological origin not merely explains the universal feature of known skin effects, but also leads to new types of the skin effects, symmetry-protected skin effects. And this paper goes on to show Z2 skin effect, which is protected by time reversal symmetry. On the basis of topological, and again, there are like three essential properties being protected in these non-Hermitian spaces that underpin quantum mechanics. Anyway, very technical, very complicated, but it's a big deal to find the origin mathematically that matches these physical observations. So really great. And we're talking about a lot of people who care. It's 1,200. It's all your particle physics, theoretical particle physics. Yeah, we'll call it skin effects. Quantum skin effects. That's amazing it has 1,200. I mean, it's 1120, right? Let's not overblow it. It's 1,100. And then we looked at two more papers. The improved constraints on the primordial gravitational waves using Planck, WMAP, and BICEP Keck observations. Let me just refresh our memories on this. They're representing an analysis of a ton of experiments combined together, all the way up to the 2018 observation season. To start with, big publications from big experiments like this, and especially if you group data from multiple experiments, these aggregate studies are going to get cited more heavily than studies that just focus on a subset of the data, because the aggregate study will draw the best picture and will have the lowest error bounds on its measurements, because it draws upon a larger data set. That's the nature of error. The more measurements you get, the more certain you are of the outcome. So this could well be like the biggest paper. When did it come out? 2021. It's been out for a while as well. So having sat on the shelf now, it's gathered quite a few citations. Yeah, it's gathered quite a few citations. Let's see if we can find some powerful observations here. Unbiased search results. Strongest constraints to date on the primordial gravitational waves. There you go. And it'd be nice to know the sigma value. The likelihood analysis yields the confidence interval, 95%, where R of R for the 95% confidence interval is less than 0.036. This is a groovy tune, eh? Groovy. We're gonna love this, yeah. Okay, let me just have a quick look at the stream. Let's see if the audio is okay. Give me a sec. Oh shoot, I can't watch the stream on that tablet because the tablet's too crappy to run the stream. Tablet's too crappy to run the stream. Too crappy. But my phone isn't. Hold on a sec. Okay, level checks complete. Thank you for your patience. Thank you very much for your patience. The music was a little too loud, isn't it? And sometimes a little too weird. It doesn't have to be too weird. It can be a little weird, you know? It can be a little weird. Okay, nice. Okay, we've got some level adjustments. That's fantastic. Right, so where were we? We were identifying the top contributors to phys review letters over the last 5 years, and so far we've reviewed the muon magnetic dipole measurement for 2,200 reviews, the black hole merger, the quantum computer that compressed 8 years into 1.2 hours somehow, and lastly, the quantum skin effects paper. No, not lastly, there's 2 more. Quantum skin effects with 1100. And then some measurements on the primordial gravitational waves using a combination of measurements from the largest experiments. WMAP, BICEP, Keck. Great. Gravitational wave measurements. And that's hot topic, right? Everyone wants to know where the source of gravity is. How can we knit gravity into our existing models? So it's getting a lot of reviews. A lot of citations here. 1,044. 1,044. Okay, and then another really fundamental measurement here, the permanent electric dipole moment of the neutron. And that's 958. We'll call that 1,000 as well. Electric dipole movement of the neutron. That's huge. The neutron is so fundamental, we take for granted that neutrons appear everywhere around us, in all of the matter, tucked away in the nuclei of everything about us. Like this delicious peanut punch, for example. Rich with neutrons. Rich with neutrons. Oh god, they're so refreshing, those neutrons. Maybe it's the protons that are so refreshing. Hard to say. The measurement of the permanent... I mean, it's not that hard to say, really. If you think about what refreshment means, it's like a combination of mouthfeel. It's more molecular energy, isn't it? I'm pretty sure that it's that satisfaction is molecular. Okay, and particularly taste, because to taste the molecules themselves, that requires taste receptors, which operate at the molecular level. The binding sites require molecules of certain flavors to bind. Like peanut punch, for example. Wild, that's so good. Okay. Okay, now we end up in some fresh territory here today. Let's see what we've got. We've got the first dark matter search results coming out of the Lux-Zeppelin experiment. Does anyone know the Lux-Zeppelin experiment? I gotta say, I'm pretty ignorant about that one. The expedient. I love when chat can understand what I'm trying to say. I'm not sure what you mean by the Lux-Zeppelin experiment. Okay. How about this? Let's see, perhaps a band. Led Zeppelin? It's not Led Zeppelin. It's not Led Zeppelin. I guarantee that, chat. Chat doesn't know about the Lux-Zeppelin results, by the way. Oh, chat thinks it can give us a summary. Okay. Come on through, chat. Sheesh. You think you can do it? Okay. Do my job better than me. Let's take a look here. Some images. We've got some photo multiplier tubes here. It's identifying these PMTs located all around the chamber. This reminds me of Keck, honestly. But this is a the LZ dark matter experiment, I guess, where liquid xenon heat exchange. So they're using liquid xenon cooling and gadolinium loaded liquid scintillator. So gadolinium's a great scintillator. They use it a lot in medical physics, where I studied as well. Oh boy, there's a lot of material inside this experiment. Look at the size of it. Here's one person. So it's maybe 5 people across just inside of the liquid scintillator chamber. And then outside of the scintillator chamber, there's a huge water tank. Some instrumentation conduits come through. These instrumentation conduits are going to be vulnerable to the heat. So there's probably an extra bit of cooling here on the end cap at the top. High voltage feed through. Nice. 120 Vito photomultiplier tubes. Oh, here we go. 7 tons of liquid xenon time projection chamber with 488 photomultiplier tubes. An additional 180 xenon skin photomultiplier tubes. So they're using the xenon as another PMT somehow. Wow. Interesting. It's a dual phase xenon time projection chamber dark matter detector located deep underground at Stanford Underground Research Facility in Lead, South Dakota, shielded by about 4,300 meters of water equivalent overburden. So calling it water equivalent is just saying like there's a lot of dense material in ground there, but if you converted all of that mass into an equivalent amount of water that absorbs the same radiation, you get 4,300 meters of distance through water. So it's like 4 kilometers thick, effectively, in water. That's crazy. The first search, sometimes called SR1, used a fiducial mass of 5.5 tons of xenon and collected 60 live days of data. The target particles are hypothetical dark matter candidates called it's a WIMP search, I see. Weakly interacting massive particles. Right, so when I was in my studies in particle physics, we talked about the WIMPs as highly theoretical models. It sounds like they're finally getting to the stage where they're able to look for evidence of these WIMPs. Weakly interacting means they're not going to be bumping into a lot of the environment around them, which makes these particles extremely difficult to detect. But if you can find these particles, then you can make a strong statement about CP violation in the universe. Because there's so much missing dark matter and dark energy, finding these particles could represent a pathway to closing the door on some of the inconsistencies in our model. So what it found or didn't find. They were consistent with background only. No clear evidence for dark matter interactions. It set new upper limits. This is one way of saying it. It set new upper limits. Womp, womp, womp. Yeah, it's sad, actually. Can we get a womp, womp up in here? Sorry, no wimps. No wimps in the detector, everybody. We looked. Boy, did we look. But that doesn't mean that weakly interacting massive particles don't exist. It just means that they're even weaker than we thought if they do exist. And another way to say that is that LZ sets new upper limits on that strength with which WIMPs can interact. Specifically with nucleons in xenon nuclei. Like, it's possible that choosing xenon as an interacting medium wasn't ideal for reasons we don't know. For spin-independent WIMP nucleon interactions, the strongest limit was for a WIMP mass around 30 to 40 giga-electron volts per c squared. A cross-section less than roughly 5.9 times 10 to the negative 48 centimeters squared at 90% confidence. That is a tiny, tiny cross-section. Yeah, just compare with other major discoveries in particle physics. It corresponds to an area of 10 to the negative 72 meters squared. It's equivalent to a particle like these are smaller than Planck scales, right? So these are, I mean, they're real. It's just such a strange idea for things to have such a tremendously small scale. Small scale. These might not exist for reference. Let's just relax. Equivalent to a particle interacting with matter so rarely that it could pass through light years of material without ever being scattered or interacting, which is astonishingly small, far beyond typical electroweak interaction strengths. So what's your cross-section? Here's the orders of magnitude. Strong interactions, those are the interactions inside of the nucleus. 10 to the negative 26 to 10 to the negative 24. Electromagnetism, the stuff you and I feel at the surface, the molecular stuff, the valence electron stuff that you learned in chemistry and high school physics. Those energies, those cross-sections come at 10 to the negative 25 to 10 to the negative 30. So encompassing strong interaction cross-section, but even less likely. Weak interactions are about half the order of magnitude as these proposed WIMPs, ranging between 10 to the negative 38 and 10 to the negative 39 for weak interactions. Holy cripes. Solar neutrinos have a cross-section of interaction of 10 to the negative 44, 10 to the negative 45. Really tiny, tiny interaction. And solar neutrinos and even the neutrino background or coherent elastic neutrino nucleus scattering, all of these new neutrino-style interactions, I thought those were the lowest interaction probabilities. I thought that neutrino interactions were the least likely interactions we had, which is why experiments like the Sudbury Neutrino Observatory and Kamiokande and Super Kamiokande were only able to excel with the usage of huge vats of heavy mediums, such as heavy water, in order to flood the medium with neutrons and to slow those neutrinos down in an effort to increase the cross-section probability. The cross-section, excuse me, yeah. So this is a crazy new limit on WIMPs. If people are still looking for WIMPs, it's going to be tough to get funding for that. Here's the comparison to the production of the Higgs boson. We were able to see this at a cross-section of 10 to the negative 36 to 10 to the negative 39 centimeters squared, which is 12 orders of magnitude larger than the limit on these weakly interacting massive particles from the Lux Zeppelin experiment. God, even the detection of neutrinos, which is basically impossible, is 5 orders of magnitude larger for reactor antineutrinos. LZ's limit is comparably extreme in its domain, pushing detection to the edge of physical possibilities. So the heavy citations on this paper, which came in Phys Review in July 2023, the first dark matter search results from the Lux Zeppelin experiment. These were heavily cited because everyone was waiting to see if WIMPs were real. And there are so many physicists, both experimental and theoretical, whose direction in their research entirely depends on the outcome of these experiments. So this is huge. Consistent with background-only hypothesis, setting new limits on spin-independent weak nucleon, yeah. I mean, we're calling it what it is. This mu on magnetic dipole measurement, though, huge, right? Quantum skin effects, the quantum computer, gravitational wave measurements, electric dipole of the neutron. And now, background, excuse me, background. Background only hypothesis for WIMP. Dark matter search. And number of citations, I think we're looking at another 950 citations here. Yeah. All right, at some point we got to break these down. Okay, and we're getting down the list. Let's just take a more cursory look. We're not going to necessarily tailgate every single one of these papers. Let's just get in and see who's good. Is this from the same... We've got another paper here, correspondence between winding numbers and skin modes in the non-Hermitian system. So someone else is characterizing these skin effects. Is this a follow-up paper to the original topological origin of non-Hermitian skin effect paper? This is Okuma, Kawabata, Shiozaki, and Sato. And the follow-up is from Zhang, Yang, and Fang. So no, okay, these are separate groups. Let's see, the topological origin of non-Hermitian skin effects was published in 2020. So it had some extra time probably to soak up citations. Whereas correspondence between winding numbers and skin modes in non-Hermitian systems... Nope, same time. 2020, September 2020. And they're calling it like a winding of energy. We established the exact relations between the winding of energy, which is another way for them to frame the eigenvalue of the Hamiltonian. They're just saying the modes, the way that these systems exist, the states in which they can be, the fundamental axes from which all of its other states are built. On the complex plane, as momentum traverses the Brillouin zone, woof, we're getting thick now, with periodic boundary condition, okay, and the presence of skin modes with open boundary conditions in non-Hermitian systems. We show that the non-zero winding with respect to any complex reference energy leads to the presence of skin modes, and vice versa. We also show that both the non-zero winding and the presence of skin modes share the common physical origin, that is the non-vanishing current through the system. It gives cosmic microwave background energy. It gives vacuum energy. Apparently we're not allowed to read this paper until we pay for it. Do I have my VPN here? Hold on a sec, y'all. Hold on a sec, y'all. This one is funky. I like this. Let's get that favorited. Yeah, let me just see if I can log into my institution's portal here. No, I don't have the portal installed. I don't even have the VPN installed. It is fine. I mean, if we ever want to dig into these papers, I'll do the work. We'll pull in. I just want it to be on hand though. Excuse me. Ooh, peanut punch packs a punch. Oh, goodness. Hell yeah. What do we got here? Yeah, we've got another person fighting for skin mode observations. We've got 934 citations here. Topological Kagome metal with superconducting ground state. So is this superconducting? Is this material science here? Oh boy, does anyone know that? A Z2 topological Kagome metal with a superconducting ground state. What is... It's cesium vanadium? SB5? It's part of a newly discovered family of kagome metals that have recently attracted major attention in condensed matter physics, which combine kagome lattice geometry, which is a 2D network of corner-sharing triangles, strong electronic correlations, a topological band structure, and an unconventional superconductivity. Kagome metals naturally host Dirac cones, flat bands, and strong geometric frustration. Together, they create fertile ground for exotic electronic phases. In the cesium, vanadium, cerubandium? Like, what's SB? Does anyone know what this is? Vanadium atoms from the Kagome network are responsible for its unusual electronic structure. Listen, I don't know crap about material science, y'all, so the only thing I know about vanadium is vanadium gets embedded into high-carbon steel knives to improve the strength of the knives themselves. It's like a cheap and easy trick to strengthen a knife, but still leave it malleable enough that you could sharpen it. It replaces conventional knife materials. Okay, so what do we have here? Z2 topological metals. A Z2 topological invariant is the same type used to classify topological insulators. In cesium, vanadium, cerubandium. Can I just get the name? How do you say it? CSV3SB5. Really? CSV3SB5? They just say all the letters. Really? They just say all the letters? CSV3SB5. CSV3. They really pronounce it, eh? They really pronounce the chemical composition. I'm fine with that. It just feels a little bit, like, it's okay to be precise, but there's a place for naturalness. Like, we gave all the elements names, even though they're really just combinations of protons and neutrons. We could call carbon element 12, you know, or 16 or whatever it is. What's carbon? That's carbon. I don't know the periodic table all the time, okay? Periodic table. Yeah, where's carbon? 6 or whatever? No, it's 12. Look, it's 12 because it's got 12. It's its atomic mass. 12.011. Yeah, I guess we could call it by the number of protons or whatever. Like, they're uniquely numbered in a bunch of ways, but we also gave them names for ease of communication, I assume. It was natural at the time to do so. This is cool. Google's got a periodic table here. Is it 3D, really? Whoa, you get to see the tungsten. Wow, look at that. Wow, look at those shells. This Bohr model of the atom is very misleading. Roseline TTV, what's up? Welcome to the chat. Welcome. Tungsten's alloys have numerous applications. Yeah, so SN, is that cerubandium? Antimony. Oh, SN's tin. I see. It's tin. So we're talking about cesium and tin. Oh no, SB, it's antimony. Excuse me. CSVSB5. CSV3SB5. Antimony sulfide was recognized in pre-dynastic Egypt as an eye cosmetic as early as about 3100 BC, when the cosmetic palette was invented. Fancy. So it's antimony, and it's cesium, right? CS. Whew. Look how similar antimony and cesium are. They're so close on the periodic table. And it's also vanadium. Where's vanadium? Is it also close by? Does anybody see vanadium on the periodic table, y'all? It is an element, is it not? Is it one of these crazy elements way off the side? Nah. Nah. Literally a V. Can anybody does this say something about me? I just cannot find it. There it is, 23, vanadium. Vanadium is harder than most metals and steels even. And just look at that. Look how solid that totally misrepresentative Bohr model rendering of the atom is. Oh, for goodness sake. Look at this. So taking these and what do we generically say about cesium? It's one of only 5 elemental metals that are liquid at or near room temperature. So the combination of cesium, vanadium, which is really hard, and antimony. Antimony. What do we say about antimony? It's colorful. It was colorful. For whatever reason, a ton of antimony and just a single cesium and 3 vanadium. What does it look like? What's the structure of this atom look like? Oh, wow. Look at that. The magnetic breakdown and band topology in the Kagome superconductor cesium CSV3 SB5. I have a hard time saying that. I have a really hard time saying that. Repeated zone scheme of the 2x2 reconstructed Fermi surface for CSV3 SB5. Detail of the X2 and V orbits. And then a high-frequency oscillation spectrum. The K orbit here at the front corresponds to the sum of the X2 and V orbits. Okay. And the goal of these metals is to generate bizarre or exotic electronic interactions at that tiny, tiny atomic level. And they've got a measurement here. DHVA measurements in pulsed fields up to 85 Tesla using the tunnel diode oscillator technique. Is that a standard, I wonder, for measuring the impact or the strength of the surface's construction? Oui, c'est bien. So what do we have here? I just want to see like a rendering of the lattice structure. And here's what they're showing me. All of this antimony, all in and about tucked in, kind of supporting vanadium, a hard core of vanadium, which is itself bound in this lattice of cesium. Is this correct? Is this a real picture? It's from Argonne Laboratory. This is probably a better looking image. Yeah, look at that. The figures. Here we go. Yeah, cesium here at the main points of the lattice, and then an internal lattice sandwiched between the cesium, where vanadium makes up a plane that matches the alignment of the cesium planes. So antimony feels like a silicon bouncer, like a silicon mediator that just kind of, I mean, I say silicon because that's how I pad my hard drives, but it's like it dampens those interactions between the stiff vanadium and the liquid cesium. So are they supercooling this? Cesium's getting tight. Cesium's getting cold, but normally cesium is very loose. So it probably conforms in a real way, kind of like a lubricant around the vanadium structure. So what's the argument here? And if they drop below 2.5 Kelvin, it becomes a superconductor. There you go. Which is unusual because it coexists with charge density wave order at a higher temperature, topological band features, and possible pairing states beyond conventional S wave. Gosh, who knows what this is? So there's a bunch of reasons why they don't think that this metal should be a superconductor. But below a critical temperature of 2.5 Kelvin, actually CSV3 SB5 really takes off. Why is it exciting? It's one of the few known systems that combine the geometry, topology, and correlations. The Kagome lattice physics, topological Z2 band structure, charge density wave order, and unconventional superconductivity, which makes it a leading platform for studying topological superconductivity, pairing intertwined with CDWs, strong correlation effects in topological bands, quantum criticality, and fractionalized or chiral electronic states. Whew. I don't know how much of that is correct. Cannot verify, but the material is extremely exciting for reasons that I can't even understand right away. But those reasons have to do with the exotic electronic interactions that are possible on the surfaces of these materials and through these materials. What metrics do people measure, do scientists measure to quantify these materials? Just let me know at least how it tracks compared to others. It's the transport measurements, which probe how the electrons move, the resistivity. Oh, I see. So the resistivity, that's where the CDW, the cross something something, CDW. Charge density wave order at high temperature. Charge density wave. Metallic to charge density wave to superconducting transitions. So is that how it goes? You get like a charge density wave formation? How does CDW relate to the transition? The charge density wave is directly tied to the electronic and superconducting transitions. At 94 Kelvin, it enters the charge density wave phase. And then at 2.5 Kelvin, it becomes a superconductor entering a new phase that they're referring as superconductor. So CDW is a phase. Charge density wave? It reshapes the electronic system in which the superconductivity later forms. So it's an essential step to get to that. I guess you'd call it folding. The Fermi surface changes shape. The electronic states become gapped out. And let's see, the density of states at the Fermi level drops, which affects superconductivity. Possible breaking of symmetries. Man, you can even get breaking of time reversal symmetry locally. It kind of feels like the violation of the zeroth law of thermodynamics, right? It feels like you're changing the arrow of time, right? That's not okay locally. What happens in those spaces? No, breaking time reversal symmetry doesn't mean that you've broken time. It just means you've broken the symmetry of reversibility. It competes with superconductivity because it removes some electronic states that could form Cooper pairs. It reduces the density of states, so it can suppress superconductivity. And that's why superconductivity is relatively low temperature, because CDW is dominating at like 95 Kelvin. Got it. Okay, thank you for those extra answers, Chad. Much appreciated. So it's kind of a big deal as a material because of its resistivity. Its magnetoresistance, its Hall effect, the thermal conductivity. And some thermodynamics. I mean, they measure everything about it, right? It's specific heat. And they do. Look, they measure entropy changes in the material to characterize the order of the CDW, since there will be violation of time reversal symmetry. So it is they're screwing with the rules of thermodynamics locally in these systems using superconductivity. That's crazy. That's wild. Are we going to have superconductors just standard issue soon? Are we going to have superconductors soon? Mainstream? Not in the near term. Chat's so pessimistic. Oh, slap down. Sheesh. Oh, rude, chat. Rude. But the long answer, here I'm on a more optimistic note. Let's let chat make up for itself. Dig yourself out of this, chat. Yes, eventually. Hold on. I mean, we might have a breakthrough at any moment, but only for certain applications and not in the room temperature, zero loss, everything sense people imagine. Here's the realistic picture based on current physics and engineering. We already use superconductors, just not in everyday life. In MRIs, particle accelerators, squid magnet. Yeah, I know. I just wanted to know if we're going to have them in my phone. The bottleneck is the need for the extreme cooling. Even high temperature superconductors still need liquid nitrogen cooling, which is cheap but not simple for consumer devices. What would make it mainstream? Room temperature superconductors. Cheap cryogen-free cooling tech. A material that superconducts at 100 to 150 Kelvin and is ductile. Yeah, we'll have quantum computers using superconducting qubits early. I mean, we already have this. Cool. Weird Champ TV was up. Welcome to the chat. You've got a weird question. Let's hear it. Let's absolutely hear it. Boy, I never would have guessed that. I mean, materials science is going to make a splash in any journal. Phys Review Letters is just another magnificent journal to drop such a discovery into. And how many citations are you pulling on this material? Let's see here. 934 citations. Weird Champ TV asks, how do I get a job at, say, Lockheed, specifically in those rumored black budget classified UF research if they exist? Poof, your guess is as good as mine. I've never had a job at Lockheed before, so I don't know. But I think that aerospace tech is needed, like engineering is a basic. And if you get an internship through a university with Lockheed, I think that's an easy way to get your foot in the door. And I don't know how common those internships are anymore. Could be that it's not very common anymore. What's my opinion on UFO crafts? Are they? I mean, I don't know. Yeah, it depends on what you're referring to. There's a lot of different aeronautic vehicles that are possible that we don't have currently. But I don't. Lockheed Martin makes airplanes. Is that correct? Is it just airplanes? Okay, let's see if it's going to let me paste this. Whoa, nope. No easy way to paste this. Okay, let's just grab it. Oh, and weapons as well. Right, yeah. They make weapons as well. Lockheed Martin. Yeah, they're a huge company, aren't they? Dude, can I please just get a paste without style? There we go. Nice. It doesn't want to paste and match style. Okay, we'll type it ourselves. It's CSV3SB5. Promising superconductor. And the temperature for the critical temperature of superconductivity happens there at 2.5 Kelvin. And that scored about 930 citations. Yeah, is it good to work for a company like Lockheed Martin? I think it's a pretty high stress environment, but you're able to be at the forefront of a lot of fantastic technologies. So I don't know what the politics are like inside the organization, though. Yeah, I'm not super familiar. I know of people who have worked there, but I don't have the information about what it's like to work inside. And I've never myself tried to engage Lockheed Martin directly. It doesn't sound like my kind of place from what I hear. Like it'd be fun if you got started there a long time ago and you were familiar with it, but I think it's they really grind you. They really grind you out. All right, who else do we have here? I mean, maybe let's keep that periodic table open, honestly. That's awesome. artsexperiments.withgoogle.com. To the main arts experiments. Art sex experiments. So unfortunate, the naming. You just want to get in on some next level tech. Oh, I see, Weird Champ. I see. You want to get the secret codes. You want to know how to start your own reactor in the garage. Is that what's happening? That cracks me up. What's going on with the music? Very weird. Nice. Yeah. Honestly, I'll take it. Yeah. Okay, let's bookmark this art sex experiment. That's a cool periodic table. I love that. Okay, and now we've got some much less cited papers here, but still very highly cited. 800 compared to, say, 2100 here for the measurement of the muon magnetic moment. We've got another paper around these skin effects, these non-Hermitian boundary modes and topology. This paper, let's just check the age. The other big papers in topology were coming out around 2020. This one came out in February 2020, maybe even an early predecessor here. The other publications came out in July and September, respectively. So this non-Hermitian boundary modes and topology, let's see. Our work constitutes a general tool as well as an unifying perspective for this rapidly evolving field. Indeed, as a concrete application, we find that our method can expose novel, non-Hermitian topological regimes beyond the reach of previous methods. Got it. Indeed, we expose a direct relation between the presence of a point gap invariant and the appearance of skin modes when this gap is trivialized by an edge. All right. It's more skin effects. It's more quantum. What else do we have here? Accurate determination of neutron skin thickness of lead-208. We're doing it. We're checking skin effects. And this is 2021. Here, the reporting precision measurement of the parity-violating asymmetry in the elastic scattering of longitudinally polarized electrons from lead-208. So again, you've got these skin effects where certain standards, certain symmetries are totally getting violated, even though those symmetries would never be violated in the rest of the space. But there in that skin effect region around the neutron or around some other particle, something funny happens to the symmetries. They break down. Weird Champ asks, how much energy would you even need to move a craft like that? Is instantaneous acceleration crazy? You feel like going into material science would be the best bet. Dude, yeah, I feel like your guess is correct. If we knew more about material science, it'd be way easier to say what are the physical limits of the materials that we're working with. I totally agree. And how much energy would you need to move a craft? Well, that one I can help you with. Even though I might not have a lot of experience in craft or technology, I can tell you that the energy needed to lift something, here, let's go to ChatGPT, is equal to the potential energy that object would gain at that height and velocity, which is an expression of the total energy equations, including kinetic and potential relative to a planet like Earth. Let's just say any planet. And including rotational energy. I can tell you the amount of energy needed is a full calculation of all of the components of energy. It's what we call the translational kinetic energy. It's the gravitational potential relative to whatever planet you're close to, or planets. If you're close to multiple planets, you'll have to pay this gravitational price for every one of the planets. Rotational kinetic energy, but you're asking about getting it off the ground, right? So to move it off the ground, yeah, it's just straight up U negative GMM over R for our mass of the planet Earth. Or MGH, up to the limit of a certain height, until the gravity gets funky. And then the rotational kinetic energy. So if the UFO is spinning, for example, then you need to calculate what's called the moment of inertia, I. The moment of inertia you can think of as like the amount of spinning mass that it has. Or in other words, when you stick your hands out really far and you spin around, you have a lot of I, you have a lot of moment of inertia. But if you bring all your hands in, your body becomes very sleek in the rotational direction. And that sleekness in the rotating direction is correspondent to a really low I value. So you have like a low rotating mass, big rotating mass, small rotating mass. Not because you're physically smaller, but because the distance at which the mass is held is much closer to the axis of rotation. And that kinetic rotational energy has the same form as kinetic energy. It's like 1/2 mv squared, but it's rotating. So it uses the rotational velocity here. You'll give me a shout out to them aliens if you ever get in. Oh man, don't give them my name and don't give them my address either. No, I don't want no aliens at my door. I'm okay. I mean, I think it'd be great for us to discover aliens. I'm joking, but like personally, I don't have a lot. Like I'm just a human. I don't have a lot of emotional constitution. I barely get out of bed in the days. So I appreciate it though. Yeah, send my best regards to the folks up in the sky. Oh, look, there's a quick formula for adding all of those different energies together for an object that's in orbit. So if you want to know how much energy it costs just to have your ship in orbit, there's actually a closed form calculation that's really tight. Where A is the length of the semi-major axis. So you've got like an elliptical orbit. A is measured from like, it's not the middle, but it's like the middle of the ellipsis. Look, it's like I gotta flip over to that YouTube tab. These tabs are going to sleep. What if I put it on here? Yeah. This is a good track. We'll keep this. Do you guys notice the music drops out every now and then? We get like so intense in the math. The music's like, I'm out of here. See you guys later. Okay, what else do we have here? We're really dropping off on the citations at this point. So these could be new publications, new, very impactful publications. We've got the Einstein-Gauss-Bonnet gravity, in 4-dimensional space-time. From Glavon and Lin. 650 citations. They present a general covariant modified theory of gravity in d equals 4 spacetime dimensions, which propagates only the massless graviton and bypasses Lovelock's theorem. The theory we present is formulated, okay, and why is that important? Several appealing new predictions of the theory, including the corrections to the dispersion relation of cosmological tensor and scalar modes, singularity resolution for spherically symmetric solutions. Does anyone know what singularity resolution for spherically symmetric solutions are? I know what spherically symmetric solutions are. Those are solutions to general problems, but probably non-linear systems that have symmetry along a spherical axis. But singularity resolution? What's that? What's singularity? We're resolving the singularities themselves in the space. Like sometimes you have divide by zero issues along a space because you have poles or you have other mathematical entities where you can't make an evaluation of the space or where its value goes to infinite. And I guess we resolve those issues in spherically symmetric places. Jeez. All right, chat, give me a quick one. Just give me a quick one. It's a subtle and currently active research topic in theoretical physics. The Gauss-Bonnet term is a specific combination of curvature and variance, where R is the Ricci scalar, R mu eta is the Ricci tensor. Oh my god, the Riemann tensor. Got it. Okay. It contributes non-trivially to the gravitational field equations. Okay, we're getting somewhere. In exactly 4 dimensions, the integral of G is a topological invariant, so its variation does not affect the equations of motion. Okay, so it's kind of like a special add-on to the theory that operates independently and powerfully. Yeah, I don't know. It's something real specific. So we got math. We've got some theoretical physics showing up in Phys Review letters as usual. And it's a big deal that we've got a space. We've got a gravity. Yeah, it's a model for gravity, right? What else do we have here? We have the final results of Gerda on the search for neutrinoless double beta decays. So here we've got some experimental particle physics doing its thing. 650 reviews. Yeah, where are the big things happening? The big things happen in particle physics. The big things happen in material science. The big things happen in theoretical physics and math. Big things. Let's see, the final results, and this was published in 2020. They're searching for a neutrinoless double beta decay. Did they find it? Gerda is the germanium detector array, which searched for a lepton number violating neutrinoless double decay, whose discovery would have far-reaching implications in cosmology and particle physics. By operating bare germanium diodes, enriched with germanium-76, in an active liquid argon shield, it achieved an unprecedentedly low background index. When combined with the result of phase 1, no signal is observed after 127.2 kilogram years. Have you ever heard units like that? Mass times kilogram years? Let's go. No signal is observed of total exposure. A limit on the half-life of the neutrinoless double beta decay in germanium-76 is set at a half-life of more than 1.8 times 10 to the 26 years at a 90% confidence interval, which coincides with the sensitivity assuming no signal. No signal. And so is there a neutrinoless double beta decay? No. No neutrinoless double beta decay, sorry. Okay, what do we have here? Another dark matter search result. So competing with another, what was the number of ratings on this other dark Dark matter paper, 950. The background only hypothesis. Dark matter search results from the Panda X4T commissioning run. So we assume no signal observed, right? This was published in 2021, where they report the first dark matter search results using the commissioning data from Panda X4T. Their data set a stringent limit to the dark matter nucleus. Yeah, no significant excess over background is observed. We got some beautiful bananas. Beautiful bananas here, yeah. Oh, yeah, that shit is bananas. Then we've got the extended search for the invisible axion with the Axion Dark Matter experiment. Nothing observed. This is March 2020. Why do we have so much funding for dark matter in 2020? What was going on that we were able to publish so many results? This letter reports on a cavity haloscope search for dark matter axions in the galactic halo in a very specific mass range. It utilizes the combination of a low-noise Josephson parametric amplifier and a large cavity haloscope to achieve unprecedented sensitivity across the mass range. What does chat think about this? Just briefly. Dark matter axions, which are hypothetical particles that could make up the dark matter. In the galactic halo, the region which surrounds the galaxy where dark matter is thought to exist. Okay, news to me. Galactic halo. Ah, the dark matter halo. Amen. The experimental setup is to combine a large cavity haloscope with low-noise Josephson parametric amplifier. Oh boy. And once again, I leave the audio library and it stops playing. Let's change the settings. We'll change the settings for a moment. Is it called sleeping? Pause. Memory saver in performance. Memory saver. Okay, memory saver is off. Performance issues. Inactive tabs appearance. Always keep these tabs active. Okay, I think I fixed it. I'd love to see the experimental setup. I don't, maybe it's so small you wouldn't even know, but it's a parametric amplifier. Large cavity. How big are we talking here? Let's see if we can get some photos of what's the experiment. ADMX. It's great to donate to Wikipedia. I'm closing it because I've already donated, but it's great to donate to Wikipedia. Okay, it uses a resonant microwave cavity with a large superconducting magnet to search for cold dark matter axions in the local galactic dark matter halo. Unusual for a dark matter detector, it's not located deep underground. ADMX is a large collaborative effort with researchers from universities and laboratories around the world. It's used to solve the strong CP problem, which is also an extremely attractive dark matter candidate. The axion is the puzzle piece allowing these two mysteries to fit naturally into our understanding of the universe. Great. Okay. Let's get some photos. So here's the microwave cavity. And there's a little person down there. So it's pretty big. It's like many people tall. It's a circular cylinder, 1 meter long and half a meter in diameter. It searches for axions by slowly scanning the cavity resonant frequency and by adjusting the position of two tuning rods within the cavity. And a signal appears when the cavity resonant frequency matches the axion mass. Oh my gosh, it's cold. It's cold. 4.2 Kelvin, cooled with liquid helium. And the electric field within the cavity is sampled by a tiny antenna connected to an ultra-low noise microwave receiver. Yep. Fancy electronics, you got it. Oh, and they replaced their amplifiers with squid amplifiers, which greatly lowered the noise to less than 100 millikelvin, down from 2 Kelvin. Vastly improved the sensitivity. It's demonstrated that squid amplifier allows for quantum limited power sensitivity. Fantastic. ADMX acquired Josephson parametric amplifiers, which allow quantum noise limited searches at higher frequencies. Okay, and who else is searching? We've got a haloscope at Yale, or Haystack. They're also using a Josephson parametric amplifier. And ADMX Orpheus is a second ADMX, demonstrating the use of dielectrically loaded Fabry-Perot cavity to search for higher mass axions and dark photons near 70 microelectron volts. Okay. In 2022, Orpheus reported results on a first search between 65 and 69 microelectron volts. With hardware upgrades, they're projected to perform searches from 45 to 80. All right, so there you have it. It's more dark matter searches. There's a lot of dark matter searches. They extended the search, but no one's found anything. And we've searched now in some incredible energy regimes, but no one's stopping. They're still on the search. Orpheus, Morpheus, Scorpius, Corpius. Am I right? Snorpius, Malorpius. Welcome to chat, McMerlin. What's up, my happy Tuesdays? What else do we got? We got strange metal in magic angle graphene, so more material science. This particular material is achieving Planckian dissipation. Planckian. Is that when you dissipate energy on the Planck scale? Like really small amounts? What does that mean? That's an Eric Andre show reference. Okay, I don't know that. I don't know that reference. Hold on a sec. Am I allowed to watch that even? It's probably copyrighted, but I'll get that down for later. Some things to watch for later. The Eric Andre Show. Thank you for that, Mike Miller. Planckian dissipation usually refers to the loss of energy by a system in a way that is governed by Planck's law, or Planckian physics, particularly in the context of condensed matter physics. So it's like something about the way it's losing energy. In many materials, especially metals and strange metals, the electrical resistivity, or more generally, the scattering rate of the electrons, increases with the temperature. That makes sense to me. You get more kinetic energy and they fly off faster, more easily. Same concept as Einstein's 1905 photoelectric effect paper. The Eric Andre Show used to come on late on Adult Swim. Oh man, I used to watch a little bit of Adult Swim, but I don't remember the Eric Andre Show. Is it good? Yeah, I'm going to check it out. I hope it does still run. And there's a proposed universal limit for how fast a system can even dissipate energy, which is called the Planckian limit, which the scattering rate is 1 over tau, the rate. The relaxation time between the scattering events is approximately proportional to the Boltzmann constant, which is tiny, multiplied by the temperature divided by the reduced Planck constant. No, the Boltzmann constant's huge, isn't it? The Eric Andre Show is a satire and talk show, and honestly not sure if it still runs. Haven't had cable in a couple of years. Dude, same. Haven't had cable in a long time. That's why I'm always wondering if stuff still runs or not. I'm like, I haven't seen them syndicate on like YouTube or whatever, so I'm not going to see it if it's not on like a modern platform. And I don't subscribe to any of these, like, I used to have subscriptions to a lot of different apps to get TV, but I'm pretty much done with that. Once some of my shows got split across multiple apps, depending on the season, I totally cut the cord on that. I was like, what is this nonsense? Let me just ask. Value of the Boltzmann constant. I think chat died on us. You just started translating books, and you don't even need TV, really. Just YouTube. Oh, dude, yeah, you don't need TV anyway. And books, you don't even need YouTube, honestly. Books are fantastic, too, but I love having YouTube. I think it's great. Twitch is not bad either, but it's great. It's great to have connections, I think. Okay, I don't know why chat is totally locking us out right now, but I'm going to take it as a sign. We're not supposed to learn about the Boltzmann constraint on Planckian energy dissipation, but it's another materials science paper with 600 citations. When did it come out again? It's 2020. Huge push for tremendous material science, 2020. Man, what kind of books are you translating? That's super cool. I love the idea of translating material. It's like reading, but a little more engaging. I wish I could speak more than one language so I could translate something. Pretty worthless translator I am. Okay, what's this? Discovering physical concepts with neural networks. Let's take a look at that. Let's see. This is January 2020. And who's publishing? Rabban Itan. What's the institutions here? Oh, wow. In Zurich. Wolfgang Pauli Straße. The ETH Zurich. Let's see here. Despite the success of neural networks at solving concrete physics problems, their use as a general-purpose tool for scientific discovery is still in its infancy. Here, we approach this problem by modeling a neural network architecture after the human physical reasoning process, which has similarities to representation learning. This allows us to make progress toward... Oh my gosh. They're modeling neural network architecture after human physical reasoning process. Listen, I think this is so intuitive and correct. I cannot begin to describe the processes that humans use to learn. We know of many of them. Like when you try something a bunch in a row and then you decide to take a break and then you come back. Where's that with neural networks? Where's that? That annealing process back and forth, what I call the famous two-step. Here they approach this problem of scientific discovery by modeling neural network architecture after the reasoning process, which has similarities to representation learning. It allows us to make progress towards the long-term goal of machine-assisted scientific discovery from experimental data without making prior assumptions about the system. Okay, you say that, but our assumptions are embedded in the training data, so no, there's not going to be any AI that escapes the bias of the training data. You're convinced that alchemy is an old term for a form of quantum physics, so you translate ancient alchemy books. Oh, it's super cool you're translating ancient books. Super cool. I think it's wonderful to be replicating old materials and to try to bring them into the life. Those old discoveries are such beautiful pieces of art. Not just art, but also if AI is a tool that shows some merit, that is the collective understanding of our knowledge represents a reasoning, those old materials are extremely valuable as data points in training neural networks or in training the futures of humans in general. But I include neural networks as part of the human existence. We're basically indistinguishable in our approaches. They apply this method to toy examples, oh do they, and show that the network finds the physically relevant parameters, exploits conservation laws to make predictions, and can help to gain conceptual insights. We got a problem-solving robot. We got a physicist robot. Who is this? 2020. Ah, Germans. Fantastic. Machine learning, quantum tomography, quantum foundations, and artificial neural networks. What an intersection, honeys. Physicists are dangerous. Okay, let's go. I love that. And 2020, is that right? Yeah, 2020. January. Etienne and Renner. The first dark matter search with nuclear recoils from the Xenon NT experiment. Let's see, published 2023, a little fresher. Oh, so it's a bit of a bigger deal. But it's just another dark matter search in the form of finding WIMPs. There's also using xenon cooling, two-phase. It's another two-phase time projection chamber. They're using 6 tons of liquid xenon mass. And the search, the intrinsic KR and RN concentrations. Can someone tell me what the KR is? KR, is there a search? No. KR and RN. We're looking. KR and RN. Where are these elements? Radon. Got it. Okay, radon. Check. We know radon, one of our noble gases. It can also occur in some groundwater, like spring waters and hot springs, yeah. Radon we know as a cancer-causing agent as well. Right side, pink metal. Thank you, McMerlin. Yeah, we're doing this. We got it. Radon. Oh, man. How often do I look at a periodic table? Never. Never. These are theoretical elements to me that have, like, their own number of protons and neutrons. They have Z values. You know, they got atomic masses. I don't know where they are on some weird table. That must be a chemistry thing. KR's in the same line. Oh, thanks for the spoilers. Thank God. Where's KR? KR. No, it's not. Oh, the same vertical line. Krypton. I'm with you. Above. Yeah, we're there. Dude, there's like 100 and how many are there? 118 on this list? It's an unreal list. It's amazing to me that people have this memorized. It's amazing to me, like, because if I spit out the standard model of particles, no one's going to be able to label the standard model, right? But like anyone could do the periodic table, but it's way harder to do periodic table than it is standard model. It's like way harder. Okay, and krypton is again another noble gas here, one of the gases used in neon signs. "15 events per ton year." Okay, a blind analysis finds no significant excess. Yeah, once again, another dark matter search that yields nothing in particular. Okay. Implication. How did we all get tricked into doing dark matter searches? What is going on? Can I just ask ChatGPT? How did physics get tricked into so many recent dark matter searches? I mean, tricked is the wrong term. Get convinced. It just seems like a lot of dark matter searches since 2020, and they're getting high numbers of citations. So people in literature are looking for this literature as well. Did we kill ChatGPT today? I'm going to Gemini. No shame. Due to overwhelming, indirect, astronomical evidence. It's these astronomers, man, pushing the physicists around. I don't know about all this cosmological input. Coupled with the realization that it must be a new, undiscovered form of matter beyond the standard model. That's what's lighting everybody up. They're like, listen, this is something we've never seen before, and literally we could be the first to see it. Imagine if we could just see it. The cosmic microwave background, gravitational effects observed back in the 1930s and significantly confirmed in the 1970s showed that galaxies and galaxy clusters move faster than the gravity of the visible matter that can be accounted for. Oh my God. So we think that there are entities being governed by dark matter itself. Man, that's crazy. McMerlin says, well, there's a concept that you feel like science ignores to a high degree. The concept that if you remove the sun from the specific spacing from the Earth, then all life would cease fairly quickly. So I believe all life on this planet is based off the sun, but science doesn't study that really. Yeah, life's really complicated. Do you believe the protospermia theory? I'm like a protospermian. I believe that life came to Earth from outside of the solar system even. Although, again, like we don't have necessarily strong evidence, but from all of the things I've learned, it seems most reasonable statistically that we would have come here from somewhere else. And although it's not unreasonable to think that maybe DNA came into existence here, if it came into existence here on Earth, statistically speaking, it probably came into existence somewhere else in the universe as well, and therefore in probably an infinite number of places, and therefore is possibly able to spread from one place to another. We also have evidence that DNA can be very radiation hard. There's bacteria that live even on the inside of nuclear reactors. So I don't know. I think DNA came here from the distance, but you're right. The physicists, we focus on the physical interactions, not on the intuition of how humans came up on Earth. Actually, to be totally transparent, the physicists I met, they couldn't care less about the origins of life on Earth in a large part. Some people are interested, but mostly they wanted to know about the rules of the universe. You don't know if there's a name, but you think even if we are a product of quantum reaction of light, hence you can see the light in your eyes. Honestly, yeah, knowing that mass and energy are related directly by Einstein's equation, it tells you that there's something really funny going on in this universe. Yeah, it's very funny. Also evidence, gravitational lensing. Yeah, there's a ton of evidence for dark matter. So everyone's just lit up in particle physics. They all want to find that dark matter candidate as soon as they can so they can have the biggest, juiciest publication first. I see what's up. I see what's going on. The sheer abundance of this unseen matter and its critical role in galaxy formation. See, now we're getting down to it. Is it, do we have astronomers to blame for this? Consider the outcomes of recent experiments, dark matter searches. I just want chat to tell us that it's bad. Is that bad? I just want to hear chat say that this is too many dark matter searches. No, astronomers aren't to blame. In fact, they're responsible for providing the overwhelming, robust observational evidence that makes the existence a necessity. Honestly, I know. I'm just being mean for no reason, and it's sad that we haven't found those candidates, but the fact that we're not finding the candidates is quite telling. Mostly null results. And that's why these dark matter searches are going to go on to a second search. I know, it feels super contradictory, eh, McMerlin? I'm annoyed by it. To be fair, they are highlighting a difference in the subject. They're saying it's a necessity. There's a scientific necessity to look for this in the energy regimes where we are. And I'm saying it now. I'm calling it 100 miles away. Half or more of these dark matter experiments, I don't know where they're getting all their funding from, but as long as these governments remain solvent who are providing the funding, half or more of these experiments are probably going to go into second searches to confirm the next energy regime. Like, I would not have started these searches because I'm not an expert in where, like, in the existing dark matter literature. But whatever's being done right now to identify the WIMPs, that's not, I don't know. Nothing's coming up. Don't give up. You have to stay true to yourself in science. You have to keep looking. And when you don't find something, it's not a proof. You just keep looking. You have to keep looking. Physics is a necessity, and you blame the world when you stub your toe. Same. Highly relatable energy. Very good. Very good. Thanks, Gemini. ChatGPT, you're out. You're not even thinking about it. Look, and then I visit my stupid audio library and I get a song. Ooh, woo, woo. Okay, I'm done. Let's see, we've got the implications of Prex 2 on the equation of state for neutron-rich matter. And what's Prex 2? Laboratory experiments sensitive to the equation of state of neutron-rich matter in the vicinity of nuclear saturation density provides the first rung in a density ladder that connects terrestrial experiments to astronomical observations. Oh my gosh, this is the quantum impact of neutrons on all of the observations we make. In this context, the neutron, look, it's another quantum page, I knew it. It's a neutron skin thickness for lead-208, providing the stringent laboratory constraint on the density dependence of the symmetry engine energy. So again, we get these violations of physical laws in local places around the surface of neutrons and other places, the skin effects, and we need to rectify those symmetry breaks. And it looks like we broke through. Looks like we've modeled it finally. Nice, and they developed a value L plus or minus 37 mega electron volts, 106 plus or minus 37, which systematically overestimates current limits based on both theoretical approaches and experimental measurements. And why try to characterize these skin effects so hard? Why? Why do we care about these microscopic electronic impacts? Because we have microscopic electronics now, and physics apparatus at the quantum level, at a very small level, must be able to detect, even with bias, its own bias, so that you can delete the bias out of the result. McMerlin's been asking these AIs about plasma because of the sun, super cool, and how that plasma affects Earth. but it doesn't have a whole lot of information. Oh man, I'm pretty clueless on plasma. My understanding is plasma is another state of matter. Like it's not solid, it's not liquid, and it's not a gas. It's literally something else. Like it gives superconducting energy. But I also I've seen some plasmas. Like I've been in a laboratory setting where we generated plasmas, but I really just don't know much about plasma. Would it be helpful to get like a 10 bullet point primer on plasma itself? That would probably help me out a lot. It's an ionized gas. It's ionized gas. It's like separated, yeah. It consists of the collection of free-moving negative electrons and positive ions created when the gas is heated to extremely high temperatures, which strips electrons from their atoms. This classical language is a little old school, but I think we understand what's being said here. And unlike a regular gas, the free particles make plasma an excellent conductor of electricity, much higher energy content. The majority of the visible matter in the universe is plasma, including stars, lightning, and the auroras. Dude, it's sick that most of the universe is plasma. That's sick. Like, it's rare to be a piece of mass, or it's rare to be just like pure energy. Ah, wonderful that is. Alchemy talks about using the fourth state of matter to create the fifth state of matter, which is why you're surprised that science isn't more focused on it. Well, I think we must be lacking an observation for that fifth state of matter. Is there a fifth state of matter that's observed? You need an observation first. It's not like we're trying to discover things we've never seen. You know what I mean? What's the fifth state of matter? Oh, there is a fifth state of matter. Yeah, Bose-Einstein condensate is another state. Oh my god. Is Bose-Einstein condensate considered a state of matter? It forms when a gas of bosons is cooled to temperatures very close to absolute zero, and at the extreme temperature, particles lose their individual identities and merge into a single quantum state, the condensate, the Bose-Einstein condensate. I feel silly that I didn't really think of Bose-Einstein condensate when I thought of another form of matter. I was, someone needs to take my degrees away. And you say, yeah, and alchemy basically talks about quantum state being at normal temperature and stable to hold, basically. I would be surprised if those observations came out of those old alchemical books. I don't think that we had the technology at the time most of those books were published to understand or describe Bose-Einstein condensate, for example, because we couldn't reach the temperatures that are needed. But hearing you say that there's a room temperature condensate maybe that they discovered, that would be an amazing discovery. That would be an amazing discovery. And they might have been mirroring, and yeah, you're right to say it. They may not have even understood what they were doing, but they might have been doing something. That's possible. Yeah, okay. There is a fifth state of matter. Is there a sixth state of matter, I fear to ask? What's the sixth state of matter? Okay, the images are getting weird now. Oh no, but Google's willing to give an answer on this. It's it's a fermionic condensate. The substrate created, again, under super cold temperatures, but distinct from Bose-Einstein condensate in that it is formed from fermions, not bosons. But I didn't think that you could have a fermionic condensate because fermions don't reduce to a superposition of states at low temperature. A fermionic condensate is made of paired fermions. Oh, I see. So it's not made of individual fermions. They're paired, and then the pairs become... So it's not a fermion condensate. It is a fermionic condensate. I see. Boy, yeah, you'd have to know this to know this. It says super cold temperatures, and then it pictures the sun like it's not the hottest ball of plasma that we know. Yeah, I know. What the F actually, right? Plasma. No, plasma is super hot. It's these condensates that are super, super cold. Yeah, it doesn't have a good picture for the condensate. Do you see this? It's using like these dots. It's like, it looks like a delicious breakfast cereal, actually. And the Bose-Einstein condensate, that got a teardrop. That's nice. That's a proper condensate. Okay. It's good we're staying on top of our stuff here today. If you think about it, they're theoretically condensing radiation, which is plasma. Okay, yeah, that's how the hell do you see that? Yeah, let's just say these are measurements of the area around the test environment, I assume. So what's this? What's this? This is just another quantum skin effect measurement. Yeah. The impact of such a stiff symmetry energy on some critical neutron star observables is also examined. So they're trying to appeal to various areas here, but because the fundamental nature of these discoveries is so wide-sweeping, you don't really have to sell yourself. Okay, what else do we have? We have another phase programmable Gaussian boson sampling using stimulated squeezed light. This is coming out of the Laboratory for Physical Sciences, Hefei University at the University of Science and Technology of China in Hefei. Oh man, I cannot pronounce these names at all. I'm so ignorant. University of Science and Technology of China, Chinese Academy of Sciences. Okay. We report phase programmable Gaussian boson sampling, which produces up to 113 photon detection events out of a 144 mode photonic circuit. So this is a quantum computer, is that right? Phase programmable Gaussian boson sampling using stimulated squeezed light. It reads like quantum computer. And I'm not sure what the stimulating or the squeezing aspects are of the light here. But they show that this experiment passes a non-classicality test based on inequality constraints. And we reveal non-trivial, genuine, high-order correlations in the GBS samples, which are evidence of robustness against possible classical simulation schemes. This photonic quantum computer, Zhushang 2.0, again, I'm so bad at pronouncing these names, yields a Hilbert space dimension up to 10 to the 43 and a sampling rate about 10 to the 24 faster than using brute force simulation on classical supercomputers. Wow. So it's another quantum leap in computers. 530 reviews there. 530 citations, excuse me. Training variational quantum algorithms is NP hard. Oh, I love this. This is a study of the computational complexity of building quantum algorithms. Variational quantum algorithms. Variational quantum algorithms are proposed to solve relevant computational problems on near quantum devices. Popular versions are variational quantum eigensolvers and quantum approximate optimization algorithms that solve ground state problems from quantum chemistry and binary optimization problems, respectively. They are based on the idea of using a classical computer to train a parameterized quantum circuit. You use a classic computer to train a quantum circuit. You show that the classical optimization problems are NP hard. Okay, so trying to train the quantum circuit is NP hard, I see. Moreover, the hardness is robust in the sense that for every polynomial time algorithm, there are instances for which the relative error resulting from the classical optimization problem can be arbitrarily large, assuming that P is not equal to NP, that it's NP complete. Even for classically tractable systems composed of only logarithmically many qubits or free fermions, we show that the optimization is still NP hard, which elucidates that the classical optimization is intrinsically hard and doesn't merely inherit the hardness from the ground state problem. Wow, yeah, interesting. This sounds mathematical. I wouldn't know even how to approach this. What's the, it's machine learning with computational complexity and graph theory? That's correct. Whew. And when did this come out? 2021? Training variational quantum algorithms is NP hard. And who produced this? University of Dusseldorf in Dusseldorf, Germany. Let's see, we've got hadronic light by light scattering contribution to the mu anomalous. Okay, more magnetic moment measurement, more muon magnetic moment measurements. It sucks to compete in the muon magnetic moment space and then to get outsighted by like a factor of 2 by the main group, or like by a factor of 4. The highest cited article in Phys Review Letters over the last 5 years, period, was the measurement of the muon magnetic dipole moment, the anomalous dipole moment, and with 2,200 citations. And these poor guys, they're coming in at 522. They even had a better measurement, right? 0.2 ppm. The other measurement was 0.43. And look, yeah, this was just published more recently, 2023. So give it a little time, and it should collect some more citations. The Lawson criterion for ignition was exceeded in an inertial fusion experiment. What, the music just stops after like 8 seconds? Bad gateway. Wow, there's an error with the host. Modeling echo chambers and polarization dynamics in social networks. Ooh, I love this. 500 citations. This is coming out of Humboldt University at Berlin, Newtonstrasse. It's coming out of Max Planck for Human Development, and it's coming for the Germany ISI Foundation. Humboldt University of Berlin. Echo chambers and opinion polarization recently quantified in several sociopolitical contexts and across several different social media raise concerns on their potential impact on the spread of misinformation and on the openness of debates. Despite increasing efforts, the dynamics leading to the emergence of these phenomena remain unclear. We propose a model that introduces the dynamics of radicalization as a reinforcing mechanism, driving the evolution to extreme opinions from moderate initial conditions. Inspired by empirical findings on social interaction dynamics, we consider agents characterized by heterogeneous activities and homophily. Is it the love of people? What's homophily? McMillan asks, do I happen to be following Unidentified Anomalous Phenomena Disclosures Act of 2023? If they release that stuff, then our tech will jump. I have no idea what that is. Like most things, I'm totally clueless. Yeah, what? UAP disclosures? Is that an American thing? Homophily is the tendency for individuals to associate and form relationships with those who are similar to them. A principle often described as birds of a feather flocking together. Homophily. We show that the trend, so they're characterizing these agents by how much they like people who are like them and their heterogeneous activities. So they show that the transition between a global consensus and emerging radicalized states is mostly governed by the social influence and the controversialness of the topic. Compared with the empirical data of polarized debates on Twitter, The model qualitatively reproduces the observed relation between users' engagement and opinions, as well as opinion segregation in the interaction network. Our findings shed light on the mechanisms that may lie at the core of the emergence of echo chambers and polarization in social media. Wow, how did this get so many citations? This is an outstanding idea. And it's just like most physicists I know wouldn't waste their time talking about this. They're not that interested in the failures of humans to communicate. They're much more interested in physics, actual science. Yes, it's an us thing, and currently it's still going. It's a US thing. I see, the UAP. It's scheduled to be released in 2025, as long as it doesn't get waved away. Okay, let's find out and see. Let's find out and see. I love the possibility of that release. Let's see here. So that's some social modeling. Sensei, direct detection results on sub-giga electron volt dark and other dark matter, quantum error correction in scrambling dynamics and measurement. Here's another article on the skin effects, quantum skin effects. I bet you they say the word skin effects. I bet you they say the word skin here. Nope, they don't. What are they talking about then? We analyze the dynamics of entanglement entropy in a generic quantum many-body open system from the perspective of quantum information and error corrections. We introduce a random unitary circuit model with intermittent projective measurements. Good God, what is going on? Our work shows that information scrambling plays a crucial role in understanding the dynamics of entanglement in an open quantum system, and it relates the entanglement phase transition to changes in quantum channel capacity. Is that fundamental? Yeah, that's kind of a big deal, but just very specific. Quantum error corrections? More skin effects, charge density waves, and electron properties. And another Kagome metals publication. Which is the metal? Potassium, rubidium, and cesium. And what are they doing here? The electronic and structural properties by first principle calculations. We reveal an inverse Star of David deformation as the 2x2x2 CDW ground states of the Kagome lattice. The Kagome lattice shows softening, breathing phonon modes, indicating the structural instability. However, electrons play an essential role in the CDW transition via Fermi surface nesting and Van Hove singularity. Okay. Kagome metals, man. Wild. And they're just looking for those transition energies through the Kagome metals. They're just looking for curious electric behavior. You think these studies starting in 2023 about these weird topics are because we've seen examples of ships that use technology that we don't understand. Okay, I don't have any observations of ships. I don't know any so far. But given how much dark matter searching is going on, that's just a physics thing. I'm not sus about that at all. And these electronic searches, this all has to do with making money in electronics technologies. It would be nice if we were inspired by something external, but I doubt that that is the case. I think it's internal still. Who knows? All of the physicists I knew where I can confirm they were personally motivated by their by reaching for the next answer, not by some conspiracy. That's for sure. I mean, it is a conspiracy in a sense. It's like, why is everyone driving for these answers? Why do people need to know why? Why is that? In a very real sense, it's like a conspiratorial energy that drives us forward. It's not a conspiracy. We still use observations. But why is it that these physicists are so driven to see the answers? I don't know. Searches for the new physics, searches for the heavy Higgs boson decay. And now we're getting into the article range. Yeah, this is like 40 to 60. And the number of citations here has really dropped off. We're down to like 400. So many of these are going to be newer articles. That's interesting. Lot of, oh man, yeah, just a lot of quantum modeling here. More superconduction. Interesting. Well, 2 hours. My brain is absolutely mush now after reading through Phys Review letters. What a crazy time. What a crazy time for research. A crazy time to be alive. I gotta say, the most impactful research that I see in Phys Review letters are the quantum computers, the demonstrations, and the measurements, the theoretical limitations on the training time and the complexity of algorithms that will get us the quantum computing we need. Looks like it's NP complete. These are long computation times. You've sat and thought about it, and then that's what drives you to translate these books, is because you're sure that it's lost technology due to misunderstanding. Yeah, that's such a romantic idea that these are lost technologies. I think that's such an optimistic perspective, that we've discovered it before and that we've lost it. I don't know if we're that. I don't know if we're that advanced. I think we might be discovering for like, maybe for the second or third time though. Like if you go back far enough. It's just that humans don't show up in the geologic record until very recently. And if you go backwards into the geologic record, that's where honestly, there's the weakness in my argument. I'm trying to use the geologic record to talk about who has been around here, but nothing has been more controversial or misunderstood than the geological record on Earth. So I should just back right off on how long people have been discovering ideas. Even saying the word people is highly suggestive of a recent archaeological information. So I don't know where to stand on that. I'm no archaeologist, that's for sure. Thank you for coming out today for Absolutely Tuesday's Literature Review. Tomorrow I'll be back. We'll be doing some software development in Python based on the specifications we dropped out that we've been working on for 4 weeks. Now, I gotta say, this project is evolving in a significant way. We did get some code spat out last time. We even have a working framework to get started on. So we'll be able to start modeling that fun software that controls our stream pretty soon. And then Fridays, I will absolutely be here on Friday for Factory Fridays. I've been playing a lot of Satisfactory in private. We're going to do a Satisfactory stream one day again. But for now, it's Factorio, and we are absolutely moving items in space between Gleba and Novus. We are the Richers that own that place. So come on by. I'll try to show up at 9 a.m. I know I showed up at 10 a.m. today. I'm struggling with the timing, but I'm still going to try to show up for 9 a.m. See how it goes. I've been exercising regularly. Maybe that will have a positive impact on my ability to show up. We will see. So far, it's not working. So we'll just see how that rolls out. McMerlin, thank you for joining me in chat. Thanks for everyone who joined in chat. And I hope you enjoy the rest of your Tuesday. Oi, oi, oi.